Good morning. All right, so today we are going to start circuit analysis of diodes. Yay. Yes, finally. Okay, so the first technique, well, there are four primary techniques we're going to look at. Load line analysis, mathematical model based on the equations, the ideal diode model, and the constant voltage drop model. Okay, so there are four techniques. Load line analysis is graphical. So this is graphical. And we will see this a lot, especially as we get into the later chapters, the transistors. This one is based on the diode equations, or the diode equation. And this is by far the simplest and most versatile. And then this is an extension of ideal diode model. Okay. So we have a circuit, a simple circuit given to us with a single diode, single voltage source, and a single resistor. Three components in the circuit: 10 volt, 10,000 ohms, and a standard diode. If we write a KVL expression around the circuit, we obtain this equation right there. V is equal to IDRD plus VD. So basically the source voltage is the resistor voltage plus the diode voltage. One energy source and two components receiving. Okay, so that's from KVL. I don't know, technology glitches. Yes. Simplest. Not really simple, but simplest of the four. Okay, so yes.
So is that the V on the left side of the equation, is that referring to the voltage source?
Yes, that's the voltage source. V on the left side is the voltage source. Is right here. So one source, one diode, one resistor. Yes. Yes, that is a good point. Yes. All right, so let's take a look at load line analysis. So first thing, how many of you know what a load line is? This is the first time you're hearing of the word load line, right? Okay. All right, so load line, it's a graphical analysis technique where we plot out the device characteristics and the external circuit characteristics on the same graph, or the same chart. Load line is basically the constraints placed on the device by the external circuit. An external circuit in the sense, here we have our diode. Anything that is connected to the diode is external to the diode, and so that is the external circuit. In this case, the external circuit for the diode is the source and the resistor. Okay, so load line is the external circuit constraint. external circuit constraint that is placed on our device. Okay. The major source of the constraint, of course, is all the energy sources that are present in the circuit. If you have one single source, the energy that is being supplied by the source cannot be exceeded, meaning 10-volt source. So anywhere in the circuit, you would not obtain anything more than 10 volts. That is one of the constraints, right? And so load line analysis is basically the analysis taking into account the constraints placed on the device with the external circuit or by the external circuit. It's basically the load on the device itself, hence the load line. Now, in general, what is circuit analysis? If somebody asked you what is circuit analysis, no, that's going into the minute details on the 10,000-foot view. Circuit analysis basically is the determination of unknown quantities. In this case, in our case, we are working with electric circuits. So it is the determination of the unknown quantities in an electrical circuit. That is circuit analysis. So in this case, if you're performing circuit analysis of our diode, what are the unknown quantities? Diode voltage and diode current. Those are the two quantities we want to determine. So analysis in this case would be determining diode voltage VD and diode current ID, right? And that is what analysis would mean for us. Determine the values for these unknown quantities. Now, if you have two unknown quantities, how many equations would we need? Right? Two equations. We have one equation, which is the diode equation, and that is already plotted right here. So the diode equation is already there. We need two equations. One is the diode equation. And if, as an engineer, if you don't have this characteristic curve, you can plot it yourself from the spec sheet of the diode. We have the diode equation. We have the parameters from the manufacturer. Simply write either in a spreadsheet or a MATLAB program, and you can plot it. So you have one equation and one plot. The second one comes from analysis of the circuit, which is what we obtained in the previous slide, right here, this one. V is IDR plus VD. Okay. So that second one is what we obtained by applying KVL. Okay. V is equal to ID times R plus VD. So far, so good, right? So right now it's a diode, single diode. We don't have more than three components, one energy source, one current limiting resistor, and one diode. So it's a very simple circuit, so to speak. When we get to transistors, we'll use the exact same technique, load line analysis of a transistor circuit. We will do the same thing. We have the transistor characteristics, and we'll plot the load line on there. Okay, so this technique is kind of important in the sense we'll see it again and again. So we have one plot, and we have the second plot. The intersection point of these two plots is our solution. I don't know what's happening with the screen right now. Let's see. Nothing's been changed since Friday. No. It should just work, hopefully. So as I was saying, the intersection point of these two plots is the solution. That intersection point will give us the value of the diode voltage and the diode current for this circuit. Okay. That point is also known as the Q point. The Q stands for the word quiescent. Or simply known as the Q point. This is another term that we will see again and again. A Q point or quiescent. Q comes from the word quiescent. Quiescent means dormant. Okay, it is present but dormant state. And the way it applies to electric circuits or electronic circuits is that we are applying a DC voltage to our device. So our circuit, our device and our circuit is ready to accept any AC inputs. Okay. Electronic devices, we are always working with both DC as well as AC. When we apply DC, we are setting up the stage for the circuit to accept an AC input. And we call that process as biasing. We are biasing our device and our circuit at a particular point, depending on our application, of course. And so the Q point refers to the dormant state of the circuit where it is present and lying in wait, so to speak, for the AC input to arrive. So in this case, if you notice, a circuit has only a DC source, right? So we are biasing our diode to operate within a certain parameter, within a certain constraint. Okay. Right now, we are not introducing an AC circuit, AC source yet, not just yet. Okay. That will come later. So again, Q point is basically the operating point, the quiescent point where our device is forced to operate. And so for Q point, we can state the diode voltages and the diode current as IDQ and VDQ. The diode voltage and the diode current at the Q point, just a subscript that is added on. And again, the same thing will apply again to other devices also later on. Okay, so when you see a subscript of Q, it refers to the Q point, or it is also known as the operating point. Operating point. And the point, the term point refers to the point on the graph. All right, 10-second pause. Think over it. Let me know if you have any questions.
Diode referring to like the diode and
the diode equation, yes, the diode equation. So the diode equation, and you can write it as the load line equation. So you have two equations. One is the diode equation, the other is load line equation. We plot them, and the intersection point is our Q point. Any other questions? All good. Okay. All right. So let's plot this out. Our load line equation is, I'm going from here to here. V is IDRD. Sorry, not IDRD. IDR plus VD. Now, if you have two unknown variables in an equation, the best way to solve it is by making an assumption of the value for one of them. So in this case, if I assume, and the best assumption value is 0. So if I assume ID is equal to 0, I can find a value for VD. And if I assume a value of VD is equal to 0, I can find a value for ID. Then I would have 2 points at the end of my graph, and I can plot a line connecting those 2 dots. And that's how I would have my load line. So when ID is equal to 0, VD would be equal to V, which is 10 volts. Straightforward, right? When you have an equation with two unknown variables, you have to make an assumption. You assume a value for one, find the value for the other one. In this case, we have two unknowns, ID and VD. Choose ID as 0, find the value for VD. Next, choose the value for VD, choose 0, and then find the value for ID. So if VD is equal to 0, then ID would be equal to V over R. That would be, oh, sorry. Yeah, V over R, which is 10 over 10,000, gives me 1 milliamp. Okay, 1 milliamp. So far, so good. But if you look at the chart only extends up to 6 volts. So you want to find a point that is closer. So we can assume instead of 0, we assume VD is equal to 6 volts. And then ID would then be 4 divided by 10,000, 0.4 milliamps. 10 minus 6. So I skipped over there. V minus VD over R will be 10 minus 6 divided by 10,000. And then simply join the points. So that point would be here. And this point is, of course, here. Join the line. The intersection point is the Q point, which is right there. Now, reading the values from a chart is literally, we're just eyeballing it. Okay, so you want to develop your skill in trying to eyeball the values. In this case, I can mark as 9, right? That point is 9. And if I want to be generous, I would say it is halfway between 9 and 1, or 9 and 10. To my eyes, it looks as if it's slightly less than half. Slightly less than half. But again, that's from your perspective, right? To me, it seems slightly less than half. But anyway, even if you take it as half, it would be about 9.5. Okay. I would take 9.4, maybe 9.5. The point I'm trying to make here is, in a quiz or an exam, if you're solving this as an engineer and you're eyeballing this, you might want to expand or zoom into that spot a little bit. Okay. If it's 9.4 or 9.5, I would mark it correct. If it's 9.6, it seems a little bit more further away from that spot. So then you might lose points. So you want to be a little bit careful about that. Having said that, I would not be giving you a problem that would be that ambiguous anyway. If I do provide a chart, there will be a certain range of values, that would, there would be a tolerance in the answers. Okay, so you should be fine. So in this case, as I said, we can take 0.95 milliamps, right? This is about 8 into 10 raised to minus 4, so 0.8, and take 0.9. The accepted values, in my opinion, so IDQ, I would state ranges from 0.95 to 0.94 milliamps. Okay, 0.95 to 0.94 milliamps. And then VDQ, let me scroll. VDQ is about 0.5, just above 0.5. So again, if I was being generous, I would say maybe 0.51. So I would say 0.5 volts to 0.51 volts. Okay. And there is no easy way for me to zoom in here actually. Oh, this is 1. So it's about, let's see, 0.5. And if I mark See, 1, 2, 3, 4, 5. 0.6, sorry. So definitely not 0.5. So definitely more than 0.5. So 1, 2, 3, 4, and 5. It's about 0.6 or less, I would say. 0.6 or less. My eyes are not that good anymore. Well, my eyes were never good, even as a kid. So, but that's as best as I can get. All right. Does that make sense? Load line analysis. Okay. Let's take a pause. Let me know if you have any questions. Yes. That's 0.5. I think it's on the other side of the line. So definitely not 0.5, I would say. Yeah. Yeah. So it depends on what kind of job you do, but you would be using graphs. No, this would only be one thing, right? A company is not going to let an engineer just decide based on one simulation or one calculation. More likely than not, there'll be multiple engineers doing the same thing, verifying the answer all the time. So eyeballing is like, it's like a quick and easy analysis technique. Yeah, exactly. So we have just enough time. I want to get into this this is going to take a while, so I'll leave that for next class. Ideal diode model. I want to talk about at least what the ideal diode model is. Okay. So ideal diode model is a third technique, but again, it doesn't really matter which one we do first. So in an ideal diode model, the word ideal itself indicates that a diode would not need a voltage to overcome the built-in potential. Meaning, if the voltage is slightly greater than 0, then the diode is on. If the voltage is less than 0, the diode is off. Okay. So in an ideal diode model, we would say diode is forward bias, the diode is on. If it is reverse bias, the diode is off. And because it's an ideal diode, right? The model we use an ideal diode, because it's an ideal diode, VD has to be just slightly greater than 0. Okay. So if you apply a voltage to the diode that is slightly larger than 0, diode is on. When the diode is on, we replace it with a short circuit. So let's mark out the points like right here. Behaves like a short circuit. And when it's off, it behaves like an open circuit. Okay. And when it's actually, you know what, this is wrong. Source voltage, that should be a source voltage. Source voltage greater than 0 volt, diode turns on. So the diode turns on, it's a short circuit. If it's a short circuit, what is the voltage between those two terminals? 0. The voltage is the same, so voltage across that diode would be 0 volts. And ID would be, well, whatever the circuit condition is, so it's maximum. But when it's off, no connection. And so because it's open, no current can flow, and so ID would be 0. Let's do it this way. Okay, ideal diode model assumes that 0.6 or 0.7 volts is not required to turn it on. It simply assumes as long as the source voltage is slightly larger than 0, diode is on, you replace it with a short circuit. On the other hand, diode is off, it's open. So when it's short, voltage is equal to 0. When it's open, current is equal to 0. All right, we'll end class here today, and I'll see you all on Wednesday.